Okay, good morning, everybody. I hope everyone's having a wonderful day. So first, welcome, happy Monday. Hope you had a good weekend. Before we get started, I wanted to just give you a couple reminders, and then I'm going to briefly talk about the assignment. And if you have any specific questions you want to ask, more than happy to answer those. But keep in mind, if you're really having some trouble with something, just don't hesitate to, give it obviously some thought, but you're more than welcome to send me an email if you want clarification about a problem, or if you have a question, just stop by my office hours. I'm more than happy to help you out, okay? So first, two things. Assignment 1 is due by the end of Monday next week, so the 27th. So just be aware of that. I've given you a while to work on this. So I'm expecting you to have that in. Remember, there are no extensions to the deadline. But as I said, although on paper it says it's due by 11:59 p.m., if you really just, they say there's some technical issues or something, and you need a little bit more time to submit, the submission will be open till, I think, around 7 in the morning, 7 in the morning the following morning. So just keep that in mind. That is just for courtesy in case, because obviously I'm not going to be able to, if I'm sleeping, it doesn't really defeats the purpose to be like, oh, it's due to midnight. But on paper, it's 11:59, but just be aware the submission will be open. I won't penalize you if you submit, say, 12:05. Just be aware of that. So if you're you try to send me an email at 11:55 and you're like, oh no, I can't submit it on time, I need another hour or something because my internet crashed or something, don't worry. It will be open for the remainder of that evening into the morning. So about, I think I said it for around 7, 6:30 or 7. If you want, I can always clarify that amount of time if you would like me to. I can always clarify that. But regardless, if you do have any issues of that nature, do let me know as soon as possible. Because obviously we're working remotely, so sometimes these things do hiccups, kind of stuff happens. But remember, no extensions. So make sure you make yourself time to make sure you can submit it safely over the internet, okay? Other thing, I've noticed that there's plenty that still haven't done the onboarding quiz. Make sure you do the onboarding quiz. I want you to do it by the end of September, the end of the 30th of September. That's where I've set it to, I believe. So make sure you do this onboarding quiz, because remember, we're using this Proctor Track business for the midterm. So I want to make sure that you've done this so that the Proctor Track software at least could register you in. You have to do this for each one of your classes. But I'll also be probably putting out a practice quiz, just it's not going to be worth marks. It's just something to get you a flavor for the kinds of, just so that you could see what this looks like, so that when you actually do the midterm, it doesn't feel as anxious or anything like that. It's just something so you can see what kind of answers you might be providing or something. I'm not going to make it for marks or anything. It's just something that I would like you to complete when we get closer to the actual midterm. But I'll talk more about that when we get there. So, are we okay with both of these? Just want to make sure everybody knows about these two important dates. Okay, so I want to talk briefly about assignment 1. Let me see. So a question about scanning pages. Let me just grab my mouse, just because the font on my chat window is only so big. So we're gonna have to scan. So answer about scanning pages for written work. Everything will be done over the quiz module for this midterm, at least as far as I'm aware at this stage. If there's anything that deviates from this, I will let you know well in advance. So for example, I might open a submission for you to submit say any scratch notes or something like that. That's something I am still thinking about. But the general responses, as far as I know at this stage, are all going to be done digitally over your courses on the quiz. It's going to be set up as a quiz on your courses. So, okay, great question. Does the assignment have to be handwritten or can it be typed? Either's fine. If you're writing it by hand, just make sure it's legible. Because if the TA or myself can't read it, then we can't really assess it for you. The thing I always tell students is that I can't, say, for example, if this was, your assignment and I printed it off, I can't put my hand on here and know exactly what you're thinking at that time. So remember, whatever's in the assignment is what we're going to assess. So so just be aware of that. But yeah, it doesn't matter. It can be handwritten or typed. So when you if you decide to write up your assignment, make sure you scan it or take a good quality picture. Remember, you're going to be submitting this as a single PDF file. So you're going to make sure, if you're going to do scanning, make sure you make all your scans of all the pages. Or if you're doing this type, make sure you save it as a PDF file, and that'll be what you'll submit. I'm going to be having a conversation later today with my TAs about how they're going to be doing things for marking. And things are generally going pretty well on my end when it comes to this. But yeah, answer, either is fine. Just remember that at the end of the day, when you're submitting, you're going to be submitting me a single PDF file. If you have any technical issues with this kind of stuff, you need to let me know well in advance, okay? Just be aware of that. So for example, if you say, I generally would expect, say, third-year computer science student to know how to make a PDF file, but if that is the case, that you're having issues, please don't hold off to the last minute. Just come and ask me about it, okay? Okay, so I see a question about the programming question. It's okay if I address your question when I get to the programming problem. I will do that. This is actually a really good question. Okay, so I'm just going to kind of boom through big parts of this this assignment. So the first few problems all involve asymptotic notation. So the first one, I ask you to prove certain asymptotic claims. So I gave you some complexity function. I ask you to prove that it's big O or big omega or big theta of another complexity function. So in these, my general expectation, remember, these are proofs you're going to be writing for me. So remember that I'm expecting you to give me an argument. So just a few tips when it comes to that. I think I gave you some tips in the assignment, but remember, just generally be clear. Try, if you're doing this, remember, you don't have to, like, when you're working on this at first, you might figure out what C and N0 might be, for example, for a big omega claim or a big O claim. And you might do this on scratch work before you write up your proof. Or if you really got the gusto to do it, you might be able to do it all in one sweep. The expectation I have is that, remember, you need to tell me what I often refer to as the game plan. So tell me your game plan. So tell me that you're going to compute C and N0 such that for all N greater or equal to N0, F is like less than or equal to the blah, 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 blah. So I want you to tell me what you're going to do. So as a part of this, that's a part of the structure of your proof. So this is to help structure your argument. So you tell me what you're going to do. So like I've done with every one of the examples I've done. And one thing is, make sure you include a conclusion when you're done. So remember, at the end of all of my proofs, what I usually do is I typically will invoke the definition of big O, big omega, or big theta, or something of that nature. For example, if I was doing a big theta proof, I would sometimes either split it into two parts, and I'd prove the big O part and the big omega part. That's okay. Each one of those, I would need to invoke the definition of each respective asymptotic notation as a conclusion. Otherwise, I won't be able to attach my game plan to the actual conclusion, which is where I invoke the definition. So this is part of the structures, these two things. And remember that when you're doing this, the goal isn't necessarily to explain to me why F is big O of G or big F is big omega of G. It is that you want to argue that F is big O, omega, or theta. So it's not that you're trying to explain it to me. You want to argue it using an argument. So notice every time I do this, I don't just say, oh, it's because it is why it is that I'm trying to persuade you. It's not just persuasion, it's that I actually give you an argument. So every time I do this, I will oftentimes select one of the constants like C, or you can even pick N0, and then I try to justify for you, using an argument, the other one. So just keep that in mind, that a proof isn't just simply me just writing down, oh, this is why because of this. That's not a proof, that's an explanation. A proof is a much more narrow version of that. It requires an argument. And you want to make it so it flows from one piece to the next piece. So So just as an example, a common mistake students will make is they'll just write down the algebra from one step to the other as opposed to adding words that connect those pieces. So just as an example, and I'm not kidding, I've seen this before, is where somebody will say, oh, I'm going to show. So you do not want to do this. so I'm going to show F is big O of G. And then all I do is I tell you what C is and I tell you what N0 is. And then I'll say, okay, well then I say F is like the left side of the inequality, like if it was, like I would say F of N is less than or equal to C times G of N, like this. I'm not even kidding, I have seen things like this in my years of doing this. You do not want to do this. Notice that I just give you C and N0, but I don't like argue anything. If you give me C and N0, just C and N0 without anything attached to them justifying why, using an argument, you will only get partial marks. You will not get full marks because I'm asking you to prove that these are the case. So remember, with claims like these, remember, you just need to show that C and N0 exists by just presenting one of each. So that should hopefully clarify this. So remember, think structure and think about an argument. And remember, don't feel like I'm expecting you to write a professional proof or anything like that. The point of this is to give you experience trying to do this for yourself. So you try your best to make a good argument, present it clear, and remember, if it's ever unclear what you're writing down, so for example, if I wrote down like X is less than or equal to Y on the board, like this, like if I just wrote that, and I told you, okay, X is less than or equal to Y, am I trying to show you that this statement is true? Am I trying to show this is false? Is the statement true? What values of X and Y is this true? You have to connect this to something, some domain, for example. For example, if I wanted to say like X is less than or equal to 1, Y is less than or equal to like 5 or something. The point is that you need something to attach the statements to. That's why we use words to connect those pieces. So just be aware of that. So that's what I would recommend generally with the first 3 problems, is remember, say what you're going to do, argue the case, so whether it be is or is not. And if you're proving, for example, a general property involving asymptotic notation, remember, look at the definition. So oftentimes when you're looking for proofs for properties of asymptotic notations, like in problem 3, recall in this one I ask you to either prove the claim or disprove it. If you're trying to prove the claim, usually the strategy will be I look at the definition of that asymptotic notation, and then I try to take each of the pieces and I try to put them together. And if I can do that in a clever enough way, I might be able to derive what I ultimately want to conclude deducively. So remember, keep in mind, this is usually my tip, is think about a game plan. So remember, just say what you're going to do. So for example, if you're trying to show that a statement is true, and then you can say, oh, the statement is true. We are going to find C and N0 such that da-da-da-da-da-da-da. And then you can say, well, observe, because this is big O of that, and this is big theta or whatever, or big O, whatever it might be, you can then say what that means for each one of them, because there's definitions for those. And then what you're going to do is you try to cleverly argue some C and N0 for your claim. So just look at the examples I do have, like we did in class and also in the notes. They may be helpful. However, if you want to disprove a claim, like in problem 3, you might have to disprove a claim. Remember, all you need is one counterexample. So what do I mean by that? So if I give you some claim, I tell you, oh, this is a property that all these asymptotic notations have. All you have to do is present me complexity functions that fail to have that property. So you just present them to me. And then all I have to do is just verify that they actually work. So for a problem like that, what I would look for is you to present me a counterexample, then explain briefly why. You don't have to get overly formal about this explanation. Remember, it's an explanation at this stage. It's not a proof. The counterexample is really what disproves it. I'm just checking to see if you understand why that would be the case. So let me just scroll down. I just want to see if there's any other questions about the first few problems. Okay, so far, are there any questions about the first few problems before I get to the last two? Am I clear? I'm trying to be clear with everybody. Because remember, it's about getting you the experience to try it for yourself. That's really what this is about. I'm not trying to be mean old Dan over here and throw you into the deep end. I'm trying to get you to say, hey, look, I can try this too. And this is one of these things, is you need to try this for yourself so that when you try this, you get more experience doing it. And by doing it more often, it helps you develop more critical thinking skills when it comes to other applications. So for example, right now we're just looking at proofs for big O. Later on in this class, we're going to look at proofs for all sorts of different things. Well, once you understand how I can take a definition and apply it, and then argue something about that definition, it makes it a little easier to talk about more complicated things. And that is an important skill computer science students typically will undervalue when they first think about this kind of stuff, because as you can see in this course, you'll notice that the way I talk about algorithms is rather abstract, but at the same time, it's also fairly concrete, which is kind of strange and odd. But when you get into that intuition where you realize, oh yeah, no, these algorithms are these things I can describe more mathematically, then the whole gates open up where you can actually start talking about algorithms in a way that provides you some guarantees as opposed to just, I write a program, it kind of works. But it's sort of, I'm trying to give you some building blocks to work with so that in your future, when you're looking at trying to say, hey, look, what am I going to do with all this stuff where you're trying to ask me to prove stuff? This is for building that mathematical backbone. And the dreaded M word, it's for some people, I know it quivers up the spine, but it's something that is a very important skill to develop, is both this ability to think a little bit more rigorously about things, but at the same time, this ability to communicate clearly. Okay, I think we're good for the first three. Problem 4. Oh, wait, I just want to double check. For problem 3, when it's like f is Okay, so I have a specific question about picking the constants for problem 3. So assuming that one of the statements was, say, true or false, I'm going to assume it's just true hypothetically. So when you select the constants, I want you to think about it carefully. So, like I said, you'll oftentimes have things like, I'll just give you an example. Like I'm not going to go into too much detail. I just want to give you like a general gist of what you might do. Just a simple sketch. So say if f is, say, big O of g like this, then, let's say, suppose I was giving you fn plus g of n, and I asked you to prove that this is big O of g of n, like this. Like, suppose I know that f is big O of g, then what I would like to do is I would like to prove that f plus g is big O of g. So what I would do with a claim like this is what we would call a conditional statement. Just like when you think of an if statement in a programming language, I'm going to assume given this, then this follows. So when you're actually trying to prove these claims, if you look and say, okay, it says if this and that, if like and this, then blank, you can use this as a given in the statement. So if I know this, then this will follow. So what I would do is I would say, okay, well, what am I trying to do? I'm trying to find. So I'm just keeping it very abridged because of the sake of time. So all I would do is I would find C and n0 such that f of n, so in our case, f would be f of n plus g of n is less than or equal to c times g of n. So what you would do in this case is you'd say, okay, well, what can I do next? Well, I have f is big O of g, so what you would do is you'd say, okay, well, f is big O of g, hence there exists C and it, so I'll give them names. I would probably call them different names just to not be as confusing. Because remember, I have C and N0 right here. I'm going to call it C1 and N1. such that f of n is less than or equal to c1 times g of n for all n greater or equal to n1. So now I have this as a given, because this is what comes from the if part of this claim. So notice all I have to do now is I can take this and try to see if there's some way I can massage this to look more like what I have up here. And that would be what you would do to determine an appropriate value for C. So you'd figure out what appropriate value for C would work, and then you would see what N0 might be. So oftentimes the strategy, as you see in some of the examples I have in the notes, where I get full proofs for a lot of the properties I talked about the other day, you'll often will see I do common things such as making N0 be the maximum of two possible values. Likewise, I could also make C be like the product of two constants, or maybe I multiply it by 2 or something like that. There's many ways you can manipulate them, but remember, it's worth noting that you can invoke constants like this, because I have this as a given, just like in some of those statements, there might be the case there as well. So I'd end up with stuff like this, and I can use these to describe a constant C and a constant N0. So that's just one idea you can do. That's one idea. But this is just a general gist. So when it comes to figuring them out, I'd recommend my best trick is just to start off with what you have. So first say what you're going to do, then look at what you're given. So if I have this and something else, I would use those facts and I could write those out using the definitions. And then I can try to see if I can manipulate those to get something new. So I'd recommend, if this is not clear, just take a look in the notes at the examples for some of the properties. Like I have like the product rule for big O. There's other ones such as the sum rule. There's plenty that are in there. I recommend taking a look at these and see how I do this with some of those examples. So that should hopefully help out with that. Does that clarify that a little bit? So just remember, if you have a conditional, like it's like if blank and blank and blank or something. These are things that the whole idea is I want to prove that if I'm given this, then I can have this. So I can use those as facts that I can use. So I just pull on them and I say, hey, look, that's true, so I'm going to do this. Let's see. Okay, how I determine the... So in that you're asking about the counter example. So somebody's asking about a counter example I had in my notes. That is pure intuition. So those I pulled out of my head. So those are something I just looked at the properties. I wrote it. So the way I would derive those myself is I would look at the definitions. And then I would say to myself, does this make sense given this definition, and this definition? So there's a bit of intuition that comes into finding a good counter example. There's many counterexamples that can exist for a statement if it's wrong. That's just, in the notes, I included a couple examples of disproving claims like this. In those cases, you just simply, it's a matter of intuition. So you'd look at the definitions, you see, does this make sense? So if it's this and that, okay, so I'm going to try my best to make it so that the entire statement is true. So the premises of it are true. So this stuff, so like I have if, this, and that, I would assume that these two things are true, but I end up with something that in the conclusion, this then part, that this is false. So in that example that is being pointed out to me at the moment, you would simply look at these and say, okay, does this work? And does that work? So if that's the case, then I'm going to proceed with those, but I want to show you that the then part is false, because in a conditional statement, if all of this is true, and the conclusion of the conditional statement, if this is false, then the whole statement's false. There's no way you can make it true. So I'm just, hopefully that helps a little bit. So the easy answer is where it came from is a bit of intuition. So you just play around with a little bit. Yeah. So if you're, for example, trying to disprove a claim, if I give you like, if F is big O of G, then this. Now, assuming that this statement was like, this is in fact true. If this was, say, a false conclusion to this conditional statement, what I would like to do is I would like to make it so that the whole statement's false. So all I do is I pick one of these that's true. So sorry, I try to get this so this is true, and any following parts of my I don't want to come up with the fancy words. I'm trying to keep this simple here. But everything that follows before the then. If I have all of these being true and I show that this following part that follows from the conditional is false, the whole statement's false. Okay, no worries. Okay, so that's the first few problems. The last two, I just want to make a couple of remarks. So for problem 4, this is the one where I ask you, so given an array of length n, I ask you to determine for me whether all the elements in that array are distinct or not. So meaning that there is a duplicate or there are no duplicates in the array. So if there is a duplicate, then you return true. If all of them are distinct, as in they're all unique, then you'd return false. So your job is to design me an algorithm that solves this duplicate problem. So I give you any array. Your job is to then give me an algorithm that correctly tells me true or false. True as in there is a duplicate in the array, false as all of them are unique. So in this, I must stress that there are many ways you can solve this problem. So I am not looking for only one specific algorithm. So some students will have different answers than others, and that's fine. So I must stress, I'm also not looking for the most efficient algorithm for this. It has to be correct though. And you must be able to analyze it for me. That's the other part of it. So you can't just like throw something at me and be like, I have no idea what it does. You need to make sure everything's clear. So for the first part, when you're writing out pseudocode, just make sure it is something that looks kind of like the things you've seen up to this point. I will not, and I must be clear, I want to encourage you to write pseudocode. If you want to include a couple sentences just explaining what your algorithm does, you're welcome to do that. It is not required. However, if it really is like, if say you're really having a hard time, just like, it's like absolutely brutal for you to figure out like, oh, okay, how can I write this in pseudocode? Just this time, I will be okay with you giving me something that looks like C++ or something of that nature. But but it has to be clear. But I really want you to give me pseudocode. So if the TA is marking your assignment and you see, try doing pseudocode next time, just be aware that we're going to be looking for pseudocode in the future. So just look at the examples I have in the notes if it really is just not clear how to do things. So for example, if you're like looking for an assignment, and also keep in mind, there is not like one universal standard for pseudocode. It has to just be something that, like if I were to look at it, I have to be able to understand it. So very often I'll use for assignment things like this arrow like that. Some people like to use a colon with an equal sign to also talk about assignment. I think I mentioned some of these things in a previous lecture. But there is not, so just make sure it's something that's very easy to read and make sure that there are no typos in your pseudocode. Because I'm going to be telling the TAs, if you don't understand it, start taking marks off. Because the point is I want to make sure that you clearly communicate the algorithm through pseudocode. The first part, give me some pseudocode. Then for the proof of correctness, the big thing is, remember, you have to be able to show me that it terminates in finite time and it produces correct output. Remember, like I said, this is an opportunity to learn and try for yourself to write a proof of correctness. So like I said, I'm not looking for Rembrandt's beautiful painting. I'm looking for what you think means for the algorithm to be true. So we're going to try arguing that is true mathematically. So I gave you a couple of examples. So I've done those, for example, examples of direct proofs. The proof of correctness depends a lot on the algorithm itself. So for example, if your algorithm is like a nested loop, the technique I did in class might be very applicable. So what you could do is you could try to observe some property of your algorithm and you try to break it into 2 possible cases that could happen, or 3 or 4. I don't know how many cases it might be. It depends on your algorithm. And then all you do is you just tell me what happens in each case and you try to argue that the output is in fact going to do what you say it's going to do. So you could give that a try. If you want to try using mathematical induction, like in one of the examples I have in the notes, you're more than welcome to give it a try. Just be careful. The TAs, I've told them that the proof has to be correct. So the part I imagine most students will have the trickiest time with is the correctness part, as in like the correct output. The termination part, I imagine most students will have no problem with. It's just the parking about the correct output. I imagine that's the part you're going to have to sit around thinking a little bit about it. And that's okay if you have to think about it a little bit. Just think about, remember, you want to be clear, give me some game plan, like what you're going to do, and make sure you include a conclusion. And then remember, the idea with you do the analysis, you identify a worst case scenario, just tell me what the worst case scenario is, be clear. I think I can't recall if I asked you to explain it, but if you want to explain it, you're more than welcome to. And finally, time complexity analysis. Some students have asked me, how do I do that? You're more than welcome to pick any of the techniques I've shown you. Whether you want to take a table and you want to count the lines, how many times they happen, and you want to introduce constants, just like I did in that first example I did, you're welcome to do that. If you want to like do what I did like where I took a barometer, I measured a line and I counted how many times that happened, you're welcome to do that. Keep in mind, depending on your algorithm, you might need to pick multiple lines to count. So for example, if you have an important important part of your algorithm that runs, you need to make sure, like, okay, you make sure that you count for both things, like the thing that's the most expensive operation, then everything else. That's why usually people will try to just count all of them. Like in that case where I just introduced constants for blocks of the code, if they're constant operations. That's another approach you can use. The point is that you have to derive for me a complexity function. So you got to explain where it comes from. And so a table will work pretty well, but make sure you just give me a quick summary of what you're doing if you're going to do that. But otherwise, you're going to be giving some explanation where you derive the complexity function. Then once you have the complexity function, simplify it down to something that is easy enough for me to just say, that's big theta of this. You don't have to prove the big theta claim. Is that clear, everybody? So that's like problem number 4. I remember one thing for me is I want to make sure my expectations are clear with you. So if there's any point where it's like, okay, I don't know what Dan wants from me, you have to let me know, because I want to make sure that when you get your marks back, that it does not seem like cryptic things to you. Like why did I lose that mark? Obviously you can ask me about it, but it's just one of these things. The other thing, I want to talk about problem 5. There's somebody that did ask about this. Is that okay? Well, so just to set up for everybody, I ask you to give me, I write out 2 functions for you, and your job is to time for me how long these 2 functions take. I think I called them assignment 1A and assignment 1B. And your job is to time them. You can use C++ if you want to translate into another programming language like a Python or a Java. You're welcome to do that. Just make sure for any one of these cases you include all your source code. Just make sure you include it. Remember, don't attach as a separate file. We're going to take a look at your code, but if you don't supply that code, you're going to get 0 for this problem. It's mostly I want to make sure that we have a reference in case we need to take and run it, but also see that you did it. The other reason why is because in the 2 parts, I ask you to generate me a table, and this comes to the question in mind. So your program that you can design somebody's asking, are you okay with code written in Swift? If you want to write it in Swift, be my guest. But I would recommend keep it as simple as possible. I don't want you spending hours on end on this. Bring out the Lisp. Like I said, I'm not going to be too worried about this. The point is I want you to do an experimental evaluation of these 2 functions. So you're going to time them. Remember, I only want you to time the execution of the function, not anything around it like output, for example. I want you to time, like start your clock, run the function, then end the clock, and so on. You can do this for both of them and produce output. I'm very open-ended about how your program can be. So why? Because in part A, I ask you to create me a table. So you're going to write out a table for me with all the values of n I gave you. Now, for those that have technical limitations, like your laptop just really has low specs, you're welcome to drop the magnitude of the values of n if you need to. But remember, keep in mind that some of these n's might take a little while. That's okay. So just be patient. It depends on what your machine is like. For somebody that's like a crazy like 8-core system, this might go a little faster. My point is that your program, as long as it produces the timings for a given n, I think you'll be pretty much fine. So for example, if you want to like make it so you read from a keyboard, the value for n, just remember, keep in mind types when you're reading in the input. Remember, these values can be rather large. I personally, the way I did it is I wrote a function that runs assignment 1A and assignment 1B, and it times it for a given value of n. So what I do is I make it so it generates the whole table for me, and then all I did was I copied and pasted it, as long as it looks nice. I mostly copied and pasted it into a spreadsheet so I could plot it. But you could do it in many different ways. If you want to write a program that for like one value of n, you like make it so like you could type it in, or if you want to make it so you run it every single time, like if you make it so, oh, it's a variable in your program and you change it every time, that's okay too. What I really care about is the timings of your program for those two functions. I don't care about it generating the whole table for you. That's more of a convenience. Is that clear, everybody? So I'm not looking for the program to have a very specific structure, except for that it just times function the assignment 1A and assignment 1B. Okay? So that's really all I'm asking for. I don't need it to be some sophisticated thing, but remember, you need to present me that table. Likewise, there is a bonus mark associated with you just plotting out your table. If you give me a table and the chart matches the data that's in your table, you will get 1 mark bonus. So there's an incentive for doing that. I give you a couple tips to make this go a little faster if you needed to. Generally, remember, you have to give me the source code, your source code that you use to create all those values. The TA may comment on the results of your experiment. You may do that. Like the TA may comment on them if they seem a little bizarre. So just keep that in mind. So let's see, got a question about programming or plotting or CSV output to Excel plotting. Like, yeah, you can do that as well. So if you want to create a comma separated value like output, you can do that. Like I said, you don't have to go that far. You just need to have it so you can you compile it for a given value of n and you can run it. That's fine. That's all you need to do. That's the bare minimum you need to do. Okay? But you can just copy them. You can literally just like look at the console and just type it into your table. You could do that if you want, or you can just go wild. I recommend don't waste too much time on this if you're going to go crazy. But hopefully is that clear, everybody? The final part of that is just simply me asking you, hey, look, given your results, tell me which function performs better and give me why. And if you're really just unsure why the output you got, like the performance you got from your two functions, if they don't look like something that you're imagining it should look like, explain that to me. So just say, oh, well, I found that this this performed better than this. I didn't expect that because of blank. So if you're really just unsure why it came out the way it did, you're more than welcome to explain that. But for a lot of students, you'll probably just look at if you create the chart or you look at the table, you can look at the values just straight up and you'll probably be able to tell quite quickly which one performs better than the other. And your job will be just to explain. Give me a reason why, looking at the two functions. I'm not looking for a fancy-pantsy explanation. Just an explanation based on the two functions and what you think happens that differs between the two. Okay, is that clear, everybody? So remember, I'm not looking for the Rembrandt of computer programs, okay? But it has to do that stuff, okay? Okay, I think we're good. So if that's the case, remember, due date is Monday next week by the end of that day. Okay, so I think we're good. If you have any more questions, feel free to bug me after class or by email or during office hours. But I'm going to proceed now back to where we were last day. Now let me I just gotta see. I just gotta turn on my dolly system. There's one thing I had. It's a Monday. What can I say? Okay, here we go. Here we go. So anyways, last day I talked about lower bounds. And I was trying to introduce you to the idea that while we normally will look at algorithms and say, okay, can we design an algorithm that has this certain time complexity or space complexity? There's the opposing side where, of course, you're previously acquainted with, okay, I design an algorithm, it does this, it has this time complexity. In lower bounds, we ask the more fundamental question, does there exist an algorithm with a given number of minimum operations? For in the worst case, or you can think of average case, or in other scenarios. We're going to mostly focus on worst case here. But I wanted to introduce you to an idea, just to kind of tie everything I did last time together, and then I'm going to do one more example. So I want to introduce you to this idea of a lower bound via reduction. Now, in this course, towards the end of it, we're going to talk a lot about these reductions. So if you're looking at this, you're like, oh, that seems a little odd. We'll see it later on in the course. So I just try to prime you to the idea that we could do things like this. So I want to imagine you have two problems, pi1 and pi2. And I wanted to know, say, a lower bound result for pi2. But I know one for pi1. So the idea here is I'm going to show you that if you could use pi2 to solve pi1, you may be able to prove that there exists a lower bound result if you have one for pi1. So I'm going to first draw you a picture. So I have this picture right here. And I'm going to put it into words that we understand, okay? So if this looks a little cryptic, don't worry. So I'm going to explain it first, and then I'm going to give you an example of how we could do one of these reductions. So the first thing I want to point out is that I have two problems, pi1 and pi2. So imagine I have a problem that I have a known lower bound for pi1. What I would like to do is, now remember, we did results kind of like this on Friday. Well, we looked at, for example, finding, say, an element x in an unsorted array requires linear time, so a big omega of n time for an array of length n. We also determined that computing the maximum in an unsorted array of length n, we require n-1 comparisons, which means that it requires big omega of n time. So imagine one of these cases was right here. Say pi1 is one of these results. And suppose I want to show a lower bound result for a problem pi2. And say this is a different problem. This is the one we're interested in getting a lower bound result for. So here's the idea. So here's an idea for you. Now remember, I want you to keep this in the back of your head. Okay, if I establish, for example, say for example, I think of pi1 as computing the maximum. Which we know that there is no little o of n time algorithm. That's what we said last time. So if I just keep this in the back of your head. So if I were to tell you that this magic box, which contains some algorithm that solves any instance x of pi1, you know that if I told you that this took little o of n, then you know that this box, that whatever's in this box doesn't actually exist, right? Can everybody agree on that? Are we all good with that? Why? Because we know that that's a lower bound result for computing the maximum. If I knew that this is actually an algorithm I can use to solve pi1, which is computing the maximum. So now here's the idea. Now imagine I gave you another problem like pi2, and I told you, hypothetically speaking, that I could take a much faster pi2, and this is so much faster than the one I currently have. Like imagine this is just some part of my algorithm. And I could show you by getting help from solving an algorithm for pi2, I could solve pi1. And I assume that this algorithm is much faster. It's much faster. So I want to suppose that this maybe exists. So suppose instead I make pi2, I want to suppose pi2 is sorting. And let me explain this picture to you, because this process is kind of, it's the idea of what we call a reduction. So suppose I give you an input x, and then what I do is I do some process, which is some quick number of operations. It's fast. I use it to convert it into an instance of pi2. For us, to go from computing the maximum to sorting, it's just simply just giving you the array to another problem. So you got to look at it like, I'm trying to use this process to help me solve pi1. So I imagine I take this, I convert it into input for this algorithm for sorting. And then it produces me an answer. So this answer is an array that's sorted. Can somebody tell me, if I give you an array that's sorted, how can I compute the maximum from a sorted array? How can I compute the maximum? Somebody tell me, how do I compute the maximum from a sorted array? Look at the ending, perfect. So all I would do is I would just say, okay, return the last position of the array. So that takes constant time to do, right? So notice this part here, this is fast, I can do this. And this part is fast too, right? Surely, if I wanted to imagine, so now this is where I'm going to put everything together for you. So I want you to imagine, I told you that there is a little o of n sorting algorithm. So I want you to imagine that this, so assume that there's a little o time algorithm for sorting. So I want to assume this. You would agree with me that this I could do, this part I could do in little o of n, right? This part I could do in little o of n. So this whole box, everything that happens in relation to this box takes little o of n. Right? Is everybody following me so far? So everything involving this box is little o of n. But there's a problem here. There's a problem here. So remember, little o is where it is big, it has big O of that function, but it's not big theta. So it's a strict, you can think of it as a strict upper bound on the complexity in terms of asymptotic terms. So just as a reminder, remember that, like, if I told you that n, like n is little o of n squared, but n is not little o of n. So now there's a problem with this, right? So remember, I showed you on Friday that there is no little o time algorithm for computing the maximum, right? But what's this? What's this? This is a little o time algorithm for computing the maximum, right? So what can you conclude? Remember back to what I told you that I put in the back of my hat. I told you that if it's little o of n right here, this box, everything this box is just simply does not exist, right? So what can I conclude about this? So if I can use sorting to help me solve computing the maximum, what can I conclude about sorting? What's the, what can somebody tell me a lower bound for sorting? So remember, if this sorting algorithm existed, then I could solve computing the maximum in little o of n. So what does that mean about sorting? Can somebody tell me? Don't be shy. So remember, just think of the box. Yeah, so sorting cannot be done in little o of n time. That is the conclusion that you can take from this. So sorting cannot have a little o time algorithm. So I'll give you an arbitrary array. You can't solve it in little o of n. Why? Because I can use this algorithm, assuming this exists. So this, I'm just giving you the proof idea. I'm just writing it out here. Just orally here. So I suppose this exists. Then I could construct this algorithm for you. And then I say, okay, well, the whole thing runs little o of n. But what's little o of n? I already established that this cannot exist because computing the maximum, you can't do it in little o of n time. Therefore, there is no little o of n sorting algorithm. Is that clear, everybody? So I wanted to show you this idea. Are we all good with this? Because I wanted to show you this because later on in this course, we're going to see a lot of this idea of this reduction where we use one problem to help us solve another problem or interrelate one problem with another. So in this case, what I would say is I'm computing the maximum reduces to sorting. So just remember, the whole idea is I look at the box. I know that pi 1 cannot be, so remember, I know that pi 1 can't be solved in little o of n time. So what I do is I show you that if I had some algorithm for pi 2 that was much faster, say little o of n, then I could build you an algorithm that actually runs in little o of n time. So that means that if this did exist, which it can't because it would solve the maximum problem, right? It would solve the maximum problem. That's why we know it can't exist. It's because I could show you a relationship between computing the maximum and sorting, and I could design an algorithm that takes little o of n time if I had a little o of n time sorting algorithm. So this is one way you could derive a lower bound of big omega n on sorting. Another way, you might ask, Dan, why'd you go through all this trouble with this? It's because, quite simple, I wanted to show you this reduction technique so that you could get the general gist of the idea. I may ask you to do something with it in the future. But the other one, of course, is just quite simple. I want to show you that there is ways non-trivially to obtain what would look like an obvious bound. So the one other way you can argue this is, okay, well, if I have the length of the array n, and to sort it, I need to check each one of the elements at least once. So that's another way you could derive this lower bound on sorting, just generally. But that one is a little bit, it seems like it's like a cop-out almost, because you have to be very careful, because for some problems, just arguing that way will not cut it. But for sorting, it works. But I want to show you just this idea so that maybe I could plant this idea in your head that we could use different problems to help us solve other ones. And if I know that there doesn't exist one for one problem, there can't exist one for another one. So that being said, when we come back, I'm going to do one more example of a lower bound result. We're going to look at sorting, see if we can improve on this lower bound. So, because little o of n, that's not very interesting for us. I'm going to show you that the one that you may be familiar with is actually the best possible for a wide class of sorting algorithms. So with that being said, I want to say thank you very much. Have yourself a beautiful day. I'll see you later.